Okay, today we're going to do is we're going to take two curves, and we're going to take the area between those two curves, and we're going to revolve that around the x or y axis. So if I have a function f that's on top, I have a function g that's on bottom, and I rotate those around, you might get something like that. All right, that's the piece that you're trying to revolve around. If I were to slice off one of the pieces, here's what I get. I have that rectangle. So if I take that vertical rectangle and I rotate that all the way around, I get that that washer. Why do I get a washer? It's a hole in the middle. Where it goes. So what we have to do is you'll get better at drawing the washer shape here. So here's my washer. Kind of extract it out here and take a glance at it. You can see that I've got y is equal to 0 is the x-axis. And then I had these other parts to the washer. And I would say that drawing this type of diagram is very helpful for students. What makes up the top part of that washer? Yeah, f of x. And what makes up the inside of that washer? Well, if you want to find the area of a washer, well, first of all, what's the width of this? Dx or dy? Dx. So forget about a volume. We'll just multiply by dx, and that'll give us the volume. But if you want to find the area of the washer, how would we do that? What's the area of a circle? Right, and I'll write r as being the larger radius. And then we would have to subtract off that smaller circle, right? Pi times little r squared. If you factor out the pi value, we get pi times the large radius squared minus little radius squared. And then if you multiply it by the width, dx, that gives you the volume of one of those. So that's the axis of rotation. That's the axis of rotation. And so now I'll refer to the y equals 0. Because tomorrow we'll examine situations where you're not rotating around y equals 0. You're rotating around other lines. The distance from 0 to g of x is just g of x, correct? So this little radius is g of x. And the distance from 0 to f of x is just f of x. So the big radius is f of x. And so the formula for our volume becomes pi times the integral from a to b of your large radius, in this case f of x squared, minus g of x squared dx. These problems today look really, really cool. Like you'll see them, you'll be like, wow, that was neat mystery. Yep. Now, here's the deal. So Maddie sees this. If this is y equals 0, if we were rotating instead of around y equals 0, if we were rotating around like y equals 1, then the distance would be f of x minus 1. You're taking your top minus your bottom to find that height. And that's what we'll deal with tomorrow, but never mind that for today. Today we're just going to keep it simple and we're going to rotate around the x and y axis. So let's try to look at 3 prime examples here. First we want to start off with x squared and y squared. Okay, the graph of y equals x squared looks like this. What does the graph of x equals y squared look like? Yeah. So can you see that this is the area that's going to be kind of formed right here? Anybody just kind of trying to be a little bit insightful? Anybody can you tell what this intersection point will be there between y equals x squared and x equals y squared? Darren says it's going to be 1, 1. Do you guys agree? Well, it's hard to set them equal to each other. You do substitution. That's equal to y, so you plug in there. You get x is equal to x to the 4th. And then 0 equals x to the 4th minus x. And then factor out an x. 0 equals x times x cubed minus 1. And then the difference of cubes is x times x minus 1, x squared plus x plus 1. And so this has no solutions. This has a solution of 0, and that has a solution of 1. So you can see that the solutions here are at 0, where it intersects, and at 1. Now, here's the deal. You don't have to go through all that work if you can make a good guess. And a good guess is 1, right? So, all right, let's just do it all like that. All right, well, I'm going to rotate this around the x-axis. So I'm going to spin that. If you wanted to find the area between those original 2 curves, would you draw vertical rectangles or horizontal rectangles? You could do either, couldn't you? But since we're rotating around the x-axis, let's draw vertical rectangles. So I'm going to draw a vertical rectangle. I'm going to spin that around. And how I usually draw my washers is I usually draw the inside first. And I draw kind of that double line on the right side. And then I do the opposite on the outside. And that usually gives me a really good depiction of my shape. So now I can see my shape. I'm gonna do my work up here. I'm going to draw my washer up there as well. And I've got the inside of this washer. I've got the center of the washer, and I have the top of the washer. The center of the washer is formed by y is equal to 0. What's the inside of the washer formed by? Yeah, if you look at your picture, it's y equals x squared forms the inside. How about that top part of the washer? X equals y squared. Now, what's the width of this washer, dx or dy? Dx. So, notice what we have. If the width is dx, everything needs to be in terms of x, meaning it needs to be y equals. Here, y equals 0, good to go. Y equals x squared, good to go. X equals y squared, got to solve for y. Square root both sides, y is equal to the root of x. So I need the small radius, and I need the big radius. What's the small radius? R is equal to x squared is the small radius. What's the big radius? The root of x. Now, I understand that to many of you, you might say, well, x squared seems like it would be the big radius, and square root of x seems like it would be a small radius. But when we're dealing with values between 0 and 1, the opposite is true, okay? If you square a small value, it becomes even smaller. So let's kind of think about that way. So I'm going to write an expression for the volume of one of these washers. I have pi times, what is big R squared? Minus little r squared, x to the fourth, and the width is dx. That's the volume of one of those washers. How many washers do I want? And so we do that so easily by simply setting up an integral. Yeah, it is 0 to 1. I want to focus on that real quick. D. Weiland is bringing up this good point about kind of our limits and our bounds. When you go to determine your bounds, first of all, because it's dx, these need to be x values. And second of all, you want to go with your original area. So always focus on that original area when you're going to do your integration, set up those bounds. Okay, so 0 to 1. It's the antiderivative of x. X squared over 2 antiderivative of x to the fourth. Fifth over 5, evaluated 1 and 0. Rest is easy peasy, lemon squeezy. We got pi times 1/2 minus a fifth. Oh no, I need common denominators. 5/10, 2/10, 3 pi over 10. Excellent idea. Dylan's looking at this, and he sees that when it's on top here, you have the same shape on bottom, right? That's always going to be the case, though. So let's look at an example where Dylan might say, well, I want to double it, just so we get clear, because this is a point of confusion that comes up. If I had, say, this parabola, and it was cut there, I was looking at this area, okay? If I rotate that around, I'm going to end up with that same kind of thing right there, right? But I don't double it because you see it down here. You're going to get that no matter what because it's rotated. What I can do is if this value is -3 and this value is +3, I could set up my integral instead of -3 to 3, I could set up my integral from 0 to 3 and double it. Because this is half and half. See the difference? Okay. All right, next problem. We might be able to make before lunch. I'll at least be able to set it up. Volume between, so we got to look at the area between y equals 1 over x. What does that look like? Yep, good. You guys are so smart. X equals 2. And y equals 2. You see the area. And that's really my area right there. Okay. Where am I rotating it? Around the y-axis. So I'm going to get that kind of shape over there, right? Now, if you were going to find the area, would you draw vertical rectangles or horizontal rectangles? You could technically do either, but because I'm rotating it around the y-axis, we will draw horizontal. Shout out to Adam Nelson today. We miss you. Good question, Austin. Um, so if you want the washer to look three-dimensional, then you should shade the inside and outside opposite each other. See what I'm saying? So if you're going to shade the top here, then shade the bottom there. Yeah, so you could shade the bottom here, and then the top. It looks kind of funny when you do that, but I usually try to shade the right on the inside and the left on the outside, or I try to shade the top on the inside and the bottom on the outside. So anyway, the middle is x equals 0. What is the outside? X equals 2. What is the inside? Y equals 1 over x. What's my thickness of my washer? dy. Well, that means everything should be in terms of y, and it should be x equals. I'm good to go for my axis of rotation, but I'm not good to go here. Cross multiply 1 is equal to xy, divide by y, and you get x is equal to 1 over y, right? Okay. So what is then your little radius? 1 over y. What is your big radius? 2. So therefore, the integral from, well, we'll talk about bounds in a second, but we do pi times what's big R squared? 4 minus little r squared is 1 over y squared dy. Now I start here, and I go up to here. This is 2. This is Did you say it, Caleb? I didn't hear it. Nope. It's a half. Because if you plug in an x value of 2, if you plug in an x value of 2, you get y is a half, right? Let's integrate. This is the line y equals 2 up here. The y value is 2. This coordinate right here is 2, 2. This coordinate right here is 2, 1/2. And we're looking at the y values. Nope, nope. This one, the outside is constant and the inside is constant. Doesn't change. Antiderivative 4. 4y. What's the antiderivative of negative 1 over y squared? Plus 1 over y. So if you look at it as negative y to the negative 2, if you take the antiderivative, you get plus 1 over y. And evaluate that from 1/2 to 2. 4 times 2 is 8. Plus 1/2. Finish when you get back. Go get some brain food. Here we go. We plugged in 2, and we got 8 plus 1/2. If I plug in a half, 4 times a half is 2. What is 1 over 1/2? 2. And so we get 8 plus a half minus 2 plus 2. So this is 4. 8 minus 4 is 4. Get 4.5, which is 9.5, so 9 pi over 2. Finish up the last one. Volume of the area. Oh, wait a minute. No. You're done. Yeah. Tomorrow. Yeah, so tomorrow we are going to rotate around something other than the x and y axis. And you're going to see how that changes. No, just y equals negative 2. So the way that we find the radius is going to change. So we're going to stop there. I got a worksheet for you. You got the rest of the hour to work.